All right, our last rule is the orbital rule in our ARIO series of criteria. And this has to do with the hybridization of that atom that bears the hydrogen. So we see that in this family of carbon compounds, we have alkynes, which are characterized by a carbon-carbon triple bond, alkenes, carbon-carbon double bonds, and then alkanes, which have carbon-carbon single bonds. And this really is only going to play a role for families of compounds like this, where we have this double versus triple and single bonds. So a nitrogen series along these lines, which I'll let you practice with a little bit later, would fit this criteria. And I do want to say that most often this is the least important rule, and we don't consider it very much. But there are cases where the orbital rule will trump one of the others. And there's really one big exception to that, that I can think of, and I'll show you what that is. So if we look at these and we draw out the conjugate bases, we're looking for what's the most stable, right? So we're talking about this carbanion, and then this alkene bearing a negative charge, and then, of course, this alkane bearing the negative charge, okay? So how would we look at these in terms of their stability? Well, we look at this guy here, here, and here, and we look at their hybridization, right? So the hybridization of the carbon here is sp hybridized. It has 2 domains. The carbon here has 3 domains, so that's sp2, and the carbon here is sp3. All right, so really the only difference between these atoms is, in fact, the hybridization, right? They're all carbon, none of them are resonance stabilized, none of them have an inductive effect, and the only thing that we can use to explain it is hybridization. sp versus sp2 versus sp3 hybridization. So what about hybridization causes one or more of these to be more stable? Well, let's give you the data. So the pKa for the terminal alkyne, a terminal alkyne would be at the end of a chain, and that's the only way you'd have a hydrogen out here, is about 25, okay? An alkene is about 42, and then an alkane is about 60. So the alkyne is the most acidic, meaning this is the most stable, okay? So this is the strongest acid. Note that it's still a very weak acid, pKa 25, but it's the strongest out of all of these. And then this would be the most stable or the weakest out of this family, okay? While still a strong base, because this is still a very weak acid, so just keep that in mind, okay? All right, so this is sp hybridized. Turns out that the more s character that there is in an orbital, so sp, it's a mixture of the s orbital and a p orbital, okay? 50% s, 50% p. So this has 50% s character. 50% s. The s orbital is closer to the nucleus. It's more electronegative, okay? So this carbon, being sp hybridized, is going to have a higher affinity for electrons, and therefore those electrons will be held closer to the nucleus. That will be more stable because there's a smaller separation of the protons and the negatively charged electrons. Then in the sp2, we have 1 part s and 2 parts p, so that is 33% s character. And in our sp3, this is 25% s character. So the less and less s character there is, the less and less electronegative that orbital becomes, that atom, that hybridized atom becomes. And the farther those electrons are from the nucleus, the less stable it is, okay? So connecting the stability to basicity and acidity. So that wraps up our ARIO rules. The main takeaway that I need you to know from this is that the more stable the conjugate base, the weaker it is, and the stronger that acid is. When your conjugate base is weak, your acid is strong. Okay, and that's of course all relative to what you're comparing. So pKa at the end of the day rules, so there's no questions asked about that. But if you need to predict it based on the structural features, the ARIO rules are your place to go. So I did mention that there is one exception to using this criteria in order. Okay, so you always go atom, resonance, and nitrogen orbital, except for one main exception that I can think of. So that is ammonia and acetylene. Okay, so by the atom rule, you'd say N is more electronegative than carbon. Therefore, the NH3 is a stronger acid, which it should have a lower pKa, but it turns out that the pKa is 36 for ammonia and 25 for acetylene. So here's a case where orbital trumps atom. And this is one of the only exceptions that we're going to need to be familiar with. And I'll bring this up again when we need it. Okay? So thanks for watching this video. Reach out if you have any questions.